Yes, so let us get started. Let me share my screen. Yeah, so I hope you are able to see my screen. Uh, so today, yeah, just hold on, let me add. Okay, looks good. So today what we are going to do is we're going to talk about enhancement factor. We try to talk about scattering coefficient, how we can actually model using scattering formulation. So we are talk about scattering formulation approach, okay, and how we can use this to find enhancement factor. Okay. This enhancement factor, I've this similar example I've done it in 2D in the iSTEM YouTube video. Today we try to see do it in 3D. So uh, there's one level of complexity more as compared to what we have done in the YouTube video. Okay, so what we're going to do is we're going to develop one 3D structure, a 3D uh, rectangular block. Okay, and half of it. So we as of now, what we'll do, we'll simplify it. We don't make it air and silica substrate. We just make it air substrate, and then we make this two gold spheres. Okay, so these are gold spheres. It could be also an aluminum as well. So okay, and then we are going to pass on an electromagnetic plane wave polarized in x direction and propagating in minus z direction, and we'll see how the field getting enhanced between these two gold nanoparticles. Okay, so any questions on the problem setup?
No, sir.
Okay, looks good. So so when you want to model this kind of effects, we would not be using the port condition. So the port condition will not be using, but we will be using a scattering formulation approach. Okay, and when we use scattering formulation approach, it's very important to know that we have to apply PMLs on all the boundaries. Okay, so we have PMLs. So this would be a 3D volumetric PMLs that we need to apply everywhere, even apply in the top and the bottom. Okay, it will be acting as an absorbing domain, but this PML needs to be applied everywhere. Okay, everywhere we need to apply PML, so even in the front and the back as well. Right, so let us go forward, and let me ask you guys, how many of you guys would be doing the hands-on with me? A quick raise of hands will kind of be helpful. Okay, looks good. So I think good number of people are going to do the hands-on along with me. Looks good. So let me go to COMSOL and go to File, New. Okay, maybe this I will use this one. So you can go to File, New, select Dimension as 3D, and then you can go ahead and use optics. Within optics, wave optics, and in that you can use electromagnetic waves frequency domain again. Okay, and in the physics you can use a frequency domain or wavelength domain. Anything should be fine.
So we are not able to see the
Yeah,
now.
yeah. No, my system is this is not working. So anyway, I'm trying to.
So we need to go with wavelength
Yeah,
domain study.
yeah, wavelength domain. So model wizard, then you can go for a 3D space dimension, and then you can go for electromagnetic waves frequency domain as a physics from the optics wave optics. You can also use RF EMW interface. Both are kind of similar on these aspects as well. Okay, my system's getting a little bit more time. So yeah, so now it is working. So you go to optics and then go to wave optics and then you select electromagnetic waves frequency domain. Okay, click on add electromagnetic waves frequency domain. Click on add. Okay, then go to the study. Then select wavelength domain and click on done. Okay, so it will give us this to this initialize. It will have initial GUI. Then you can go ahead and create one block, a rectangular block with dimensions of 500, width of 500 nanometers, and breadth of 500 nanometers, and a length of 2000 nanometers, similar to what we built yesterday. Okay, what I mean is that you can build this geometry could be 500 nanometers. Okay, this geometry, this width would be around 500 nanometers. Okay, this one would be 2000 nanometers.
Sir, we need to
Okay,
change the length
please
scale.
build this. Yeah, please change the in go to geometry and change the length scale. In geometry, change the length scale to nanometers. Okay, so please don't forget to change the length scale to nanometers, and then you can create a block. Okay, just right click on the geometry, create a block having the width of 500 nanometers, depth of 500 nanometers, and height of 2000 nanometers, and click on build all. Okay, you should be able to see your geometry on the right hand side. Okay, so instead of corner you can make it center. so that your origin becomes the center of your geometry. Okay, and in this case you might need to select the domains inside, so it's more important to use a wireframe rendering. So this is the option of wireframe rendering. Okay, so we'll just wait for a few moments for you guys to enable the wireframe rendering and applying a block with this dimension. Okay, one more thing that I forgot to mention earlier, how to navigate in the GUI. If you click on left click, you can actually rotate. Okay, if you click on right click, you can pan. This is a panning, that is you just move from left to right. If you click your scroller, just press your scroller and move forward, you are able to zoom in. If you keep your scroller pressed and move backward, you are zooming out. Okay, so these are the main three things for working the GUI. And also one more thing is that yeah, that I will show in some time once you are able to assign how to assign properties to internal domains. Right, so right now you have never faced a problem of internal domains, that is, if something is inside this domain, how to assign or select those particular boundaries or domains. Okay, looks good. So now once we have developed this, what we will do is that we need to apply PMLs from all the sites. Okay, so you can apply a thickness in the layer of about 50 nanometers. Okay, and apply it from in all the directions and click on build all. You should get something like this one. So this is for the PMLs. So I'm creating one domains which is there in all the sites.
Does this create inside? So I'm Sujay.
Yeah,
Is
it's
this create
creating inside.
inside?
Yes,
Okay.
yes.
So
This is
essentially,
creating.
the area or the volume of your block reduces by 100
It's
meters in each
yeah.
side, nanometers. Okay.
Yes, yes.
Okay.
Yeah. It creates the 50 nanometer layers inside. This is because we are going to apply a PML in all these domains. So just give this thickness of 50 nanometers and apply to all the sides. Okay, any questions or doubt till now?
Excuse me, sir.
Yeah.
Sir, I'm Jansi. Sir, my
Hmm.
the length it is showing as 1. Here you're getting 10 and minus 10.
Which one?
Uh, Here in the picture,
The
sir,
length. In
the
the length.
structure. Yes,
This
sir.
one.
That yeah, yeah. Minus 10. Top and bottom it is showing 10 and minus 10, right?
Okay. In your case, did you make it center?
One.
Base as center?
Yes, sir. I have done.
Sir, that is
500,
just
500 and 2000.
No, this base have you mentioned at center?
Yes, sir, I have done.
sir, the scale would be 10 raised to 2 nanometer, so it is same 10 minus 10, right? Or
Yeah, have you? Yeah, if you put the geometry length units in nanometer.
Yes, sir. Actually, it is 10 to the power of 3 I am having. So that means it is fine. The same thing. I have
Yeah,
not
yeah,
observed it.
yeah. Correct.
Okay.
Yeah.
Yes. Yeah.
Hmm.
Thank you, sir.
Any other questions? Looks good. So the next thing is to apply PMLs on these domains. So just right click on the definition and you'll get something known as PMLs. Okay, just right click on definition. You'll get this PML. Just apply that PML on the outer domains. Okay. So one way is to select all the domains one by one, which is kind of very painful. Okay, so either you can choose it one by one, or you can just know what is the domain number of the inside domain. You can see that on the left hand side it is showing as 14. Okay, so the one that is marked as red is showing as 14 on the left hand side. Can you see it, everyone?
Yeah, yes, sir.
So you can see it over here. But this is only possible in the latest version. Actually, it's not available in the older version, this feature. So here you can see it is showing as 14, right? This is the 14, right? So this is available in recent version, or you have to manually select this domain, for example, then you got to know it's 14 if you don't know. So one way is to select all the domains manually, or you can select all domains and then remove the 14 domain. Okay, that means you have applied all the PMLs to all the boundary domains.
Sir, select all the domains and then
Yeah, just
to
choose
apply
14 and then
PMS to the specific.
remove from selection. Okay, sorry.
Excuse me, can you just repeat once? I just
Sir,
missed
could you
one.
please explain this step?
Yeah, so I need to select all the outer boundaries. Okay, so I can go ahead and
Oh,
select one by one like this. Okay, or
okay.
what I will do is that I want to know what is the central domain number. Okay, so I actually
Oh,
I can put my mouse on top of it and then scroll forward. One If I scroll forward, keep on scrolling forward, I can get my number. What is the domain number? Okay. If I use the mouse up and bottom key, then also I can actually scroll forward. Okay. So in PML need to apply to all the outer domains. Okay. So I can select all the domains, and I can remove the internal domain number 14. Just remove it.
Sir, sir, domain number 14 means is it only one side it is removing or
No,
entire?
no. 14 domain is the inner domain, central domain.
Oh, okay, sir. Yeah.
Yeah. One way to cross check it would be to again increase the transparency. Just enable the transparency. Okay, and you can just put your mouse on top of it, and you can see this green means it is selected. Okay, if you scroll forward, it becomes red. Okay, you can see that it becomes red. Red means this is not selected. If you scroll even further, it becomes green. That is from the other side. Other side actually. Okay, so that's how you can actually see whether the inner domain is selected or not. Okay, this is a transparency.
Uh, can you just repeat how you added this artificial domains?
These domains or PML,
Yeah.
do- outer domains using this layer boundaries, layer domain. So here applied layer thickness of 50 nanometers and then select all the layer position.
Yes.
Sir, just for confirmation, there are total, I think, total of 27 PML layers, with an exception of the 14th one, which gets removed in between.
Yeah, correct. Yeah,
Okay.
correct. Yeah, any questions? Yeah, any more questions? Okay, looks good. So let us. I hope you are able to add the PMLs because PMLs are very extremely important in scattering formulation. Okay, so just make sure that you have PMLs. Next is to create the spheres, the nanospheres. Okay, this is the nanosphere that needs to be created. Okay, so let us just right click on the geometry and create one sphere. Just click on build on and see where the sphere lies. Okay, it's actually by default 1 nanometer, so it's kind of very small. Okay, just try to make it 10 nanometer and then see it's somewhere over here. I can make it even more, maybe 50 nanometer radius. Okay, and then I can just move it towards the left hand side by 30 nanometers. A lot of noise coming. Uh, yeah, so looks good. So now position is 30 nanometers. Maybe I think it a bit more. 60 nanometers. I move it. Okay, yeah. So what I do is that so there is also XY view, so you can just change the different views, make it orthographic projection, so that there is no what do you say? So there's no so multiple boundaries, so it's a perfectly XY plane or YZ plane. Yeah. So here, if I use this XZ plane, then it's like it should show you some offset. So perhaps an 80 nanometers would be better. Okay. So I'll wait for few moments for you guys to add this sphere with a radius of 50 nanometers and just have an offset of minus 80 nanometers in x direction.
Excuse me, sir.
Hmm.
Sir, I'm Jansi. Sir, what is orthographic projection means? Like how it is different from other views?
Yeah, so there are two kinds of projection. If you would have learned, I think you have learned, but the engineering design, I forgot what is the another one projection. What is it known as? Which projection starts with P? I guess
Isometric.
isometric or
Isometric, sir.
sorry.
Isometric is 2 dimensional, 3 dimensional.
Perspective. Actually, we have two in COMSOL. Isometric would also be there, but perspective and projection, orthographic. So perspective is like when we see, for example, we see a road, right, and then we see the trees along the road, right, and you're so it will actually see the trees would be getting smaller as you go. Okay, so it's something like this. I don't know if you understand it. Yeah, if you see this one, this image I'm saying over here, so this is kind of perspective projection. Okay, so things are
Yes,
getting,
sir.
so there's an origin in the center and then it kind of everything is similar to that. So orthographic position is kind of a
Is it like a mirror
uh,
view, sir?
No, not mirror view. So it's just, very much different than a mirror view. Okay.
Orthographic is
So
nothing but two-dimensional things are
yeah, it is.
orthographic.
Yeah, it convert into correct. Yeah, it
Isometric is
actually.
nothing but three-dimensional view, 3D.
Hmm.
That is what
Hmm.
means. Okay, there are two
Correct. Yeah.
different types of projection. One is orthographic, other one is isometric. The other one is perspective. Isometric is two-dimensional. Sorry, orthographic is two-dimensional. Sorry, two-dimensional x and y alone. And
Hmm.
isometric is three-dimensional with respect to some angle. 3D we can be able to.
Yes, that's correct. Okay, looks good. So
Yes.
thanks a lot. Yeah. So just I hope you have created this sphere. Then right click the sphere again, duplicate it, and just write positive 80 instead of minus 80. And you can see now
Sorry,
there are
one
two
doubt.
spheres. Yeah.
So for me, that sphere is coming outside the block, sir.
Yeah. How much nanometers did you put here? 80 nanometers.
Yes, sir, minus 80.
Okay. And this block one, did you create in the center? The base position is in center.
Oh, it's I'm checking. Yes, sir, now it's fine. Thank you, sir.
Correct. Right? Okay. That's good. So I hope you are able to create this domain structure. There are two gold nanoparticle, and so what you can do is that right now we want to see what is the distance between these 2 points. Okay, these two spheres. You want to just see that you can know it is 60 nanometers because not 60 nanometers, how much? 50 minus this. Yeah, around 30 nanometers it should be. But you want to see exactly what is the distance between the two nanosphere. So you can just right click on the geometry and you can click on measure. It's kind of very important feature of COMSOL. Right click on geometry, click on measure, and click on, instead of object, click on point. Okay, and click on these 2 points. So it's actually 60 nanometers. Yeah. Okay. This is kind of very important because you need to cross validate that whatever whatever distance you are actually putting in geometry, it is really that one or not. Okay.
Sorry, sir, can you tell again from where to I missed that.
Yeah. So just but I hope you enable the wireframe rendering. Okay. And then just right click on the geometry, click on the measure, and then just go to the geometry entity level as point, and then select between which 2 points you want to do. Okay, are you able to do that? Okay, so what I can do is that instead of this, I can write it as means if you want, you can write it like 50 plus whatever the offset. But let us not experiment it now. Maybe at a later stage, I can just show you quickly how to do a parametric sweep of the distance after increasing that distance. Well, that is something else. So now let us add the materials. Okay, just right click on the material, add material from library, and I choose the air domain built in. Just double click on the air domain, and by default the air domain would be applied to all the domains including the sphere. Okay, Then you can go and you can go to the optics, inorganic material, gold. You can again click on gold, Johnson and Christie, and then just make sure that you select something like this. So you, if you put your mouse on top of it, it will show you that it's green. So this red slab is coming. Just scroll forward. Okay, scroll 2 times forward. So you see that it is selected 19 number domain, and then I move upward little bit. Then again scroll forward, and then left click again. Right. So this domain number 19 and 20 are for the two inner spheres, and that I have given it as gold. Rest of the other domains are air. Okay, I will wait for a few moments for you guys to add these material properties.
Sir, actually, sir, this is Jay Krishnan. Sir,
Yeah.
yeah, I'm not able to select those peers.
Yeah, so what you need to do is that just keep your mouse on top of it, just make it sure that it's overlapping with your sphere, and then scroll forward 2 times. And once it is maybe a red color, then you just left click on it. Are you able to do it?
No,
Sorry?
no, sir.
Oh, can you share your screen?
Yeah, sure.
Yeah. So just put your mouse. Yeah, that's good. Now listen to me. Now scroll 1 time forward. No. Don't press that scroller and move forward. Just
Okay.
scroller is there, right? So just move the scroller forward by 1 time.
Yeah,
Go again.
yeah, got it.
Now do the left click.
Yeah, got it, got it. Thank you, sir.
Okay. Yeah. Okay.
So this is not
So how?
happening in my structure. Kavita, this
Okay.
side.
What is the issue?
The
You're
same.
unable to
I'm
select
not
the
able to.
domains.
Yes. Yes, sir.
Oh, can you share your screen then?
Yes, sir.
Yeah. So first air you already no, but air you go to air again. Air material one. Yeah, select all domains. All domains selected. Okay, good. So now double click on gold. So gold actually is not even added now. So you need to first add the gold. Double click on the gold, and then you try to select the domains. Yeah. Yeah. Just move your scroller forward. No, not 11 number domain. So you again use the broom to remove it. Yeah. Sorry. Is that? No, or you can use a keyboard. Keyboard is there. Right? Up arrow you can use. Okay. Move your up arrow 2 times.
Sir, other I can select all the domains and from there I looking at the
That
numbers.
also is now you once you know domain number, then it is fine. You can use it. Yeah.
Okay.
Yeah. It's a simple way is to just move the scroller up and down. Then you can select all the domains inside.
No, what should I do, sir?
Yeah. So the tip of the mouse cursor should actually overlap with the circle. Now the tip of the mouse is not overlapping. Now it's overlapping. Now you but this again domain number 11 is selected. You again use the broom to remove that domain. Then point your mouse tip of the now you use the cursor. Do you have cursor? Do you have a mouse? Then
No,
use a
sir.
keyboard. Your
Yes,
keyboard
sir.
use the up arrow 2 times. Somehow it's getting selected. I don't know why. Yeah, up arrow you can use 2 times. Now you left click. Yeah, similar to that, you do it to select another domain. Yeah, so this yeah, for selecting is looks good. That's how it should
Okay.
be. So I'll share my screen. I hope others are also able to do it. If you're unable to do it, you can just add number 19 and 20. Just click on paste selection and add the number 19 space 20. Click on OK. Anyone else facing the issue?
Sir,
Yeah.
yeah, I'm facing, sir.
Mm-hmm. What issue are you
Yeah,
facing?
no. Could you please repeat the last one which you said, because I cannot able. I can select one sphere. It is
Okay.
19.
Mm-hmm.
One more sphere I cannot able to select. I
No,
also
you can
don't
just
have.
click on paste selection and just mention
Okay.
20 and click OK.
Okay. Okay. Thank you. Thank you, sir.
Yeah. Okay. Looks good. Okay, so I hope you are able to add air material. So here you can see 19 and 20 becomes overridden over here. Means these two domains are not been selected for the gold material. Not been selected as a air material. Is given to the gold material. Okay, looks good. Okay, next is the physics setup, that is also very important. So in this electromagnetic frequency domain, you need to change from full field to the scattered field. Okay, and if you want to give the user defined, then you need to write your own equation, that is E naught exponential minus I omega or 2 pi f t I k, that is ewfd dot k naught into t. Or if you want to simply launch the plane wave, you can use a linear polarized plane wave or a Gaussian beam, that also you can launch. Okay, any of them you can launch, right? So right now we can launch a Gaussian beam, but will the Gaussian beam, yeah, Gaussian beam will take more time, but we can try. Let us see what will happen. Let us see.
May I ask about so Sujay here,
Yeah.
the scattered field. Um, is there any significance why we move from full field to scattered field, and why exactly?
Yeah, so full field, the way to excite in full field is using ports.
Yeah.
Okay.
Okay.
In scattered field formulation, we don't get there's no meaning in applying ports actually. So basically, we use scattered field formulation to assign the source from these conditions, either a Gaussian beam, linear polarized plane wave, or user defined.
Mhm.
Okay, and from this, why we use scattered field, because it will give you extra variable now to quantify the scattering parameters. Okay, there's
Okay.
like ex, ey, ez we discussed last time. So
Mhm.
there's a new parameter which quantify the scattering field.
Okay.
Okay, which
And
is
then
not
in this
available
case,
when you do full form, full field.
and can you then in this case can you change the location of the source? Because for example, if the Gaussian beam comes from left or right or top or
Yeah,
the
so
angle.
for example, yeah, for the Gaussian beam, we will define what is the beam radius, the focal
Uh-huh.
plane along the
The
axis,
location.
and what is the
Okay. Good.
polarization. All those things will define.
Good. Thanks.
Yeah,
Sir, here we are launching the plane wave. In that case, we have
we
to
are
specify
launching a
the
Gaussian beam,
polarization, right?
actually not plane wave. We're
Okay.
launching a Gaussian beam. Means you want to launch a plane wave, you're saying?
No, no. If we, in either case, we have to specify the polarization, right? Light polarization.
Yes, yes, yes. So for example, this is linear polarized plane wave. Then you need to give the roll, pitch, and yaw angle, which will give you your polarization direction. Okay, that you can understand from here. Once you do little bit
Oh,
trial
okay.
and error, you will get to know. Yeah. With the Gaussian beam, you need to also give the direction of polarization from here. Okay, this background field means what we are giving as a source. So your source becomes the background. Then scattered field is an extra term that actually develops. Okay. Okay, so we give there are two options: parallaxal as well as plane wave expansion. That is specifically how tight the beam is converging. So parallaxal is the most used approach. Uh, then we have the beam orientation, and in this we want the beam to come from the top to bottom. Okay, so we want the beam to be launched from top to bottom, something like this. Okay, so its focus is at the center over here. So it should focus in the center over here, right? So its direction of propagation is in minus z direction or plus z direction, whichever you can mention over here, right? So if you write plus along z-axis, then it's going upward direction. If you write over here wave number as minus, then it will move downwards. Okay, so in both the cases it's a symmetry geometry, so it doesn't matter. Okay, so beam orientation you can keep it along z-axis, and beam radius you can keep it as LDA naught by LDA naught should be fine, I guess. Let me just think about LDA naught. Okay, I think the thing that we have done is that its dimension is 500 nanometers. So
Yes.
if I want to see something convergence, then it has to be a little bit more than that. So okay, so let us try with LDA naught by 2. Let us see. Uh, okay, this LDA naught we have not yet defined, so you can go in the parameters, write LDA naught as 500 nanometers. Okay, and you can again go back to your scattering field formulation and just see that it is LDA naught. The underline is actually gone. Okay, focal plane is at 0. That means it is going to converge at 0, and the polarization I've changed it to 1 in the x, so it's 100. Okay, so I'll wait for a few moments for you guys to add this domain condition. Okay.
Excuse me, sir.
Hmm.
Sir, actually, in the selection, all domains were there, no? So everything is perfectly matched layer. So it is only this scattered field is around the particles, right? Gold nanoparticles.
Yeah.
So we need to consider the entire thing, or we are only considering the particles.
No, here
I
this
mean,
EWFD interface is selecting for all the domains. You can see all the 29 domains. Okay.
okay.
Yeah,
So,
where
but we
for
are scattering. We are only talking about the particles between the particles. I mean,
no,
the
no, that is
enhancement
the
is
no, no,
between the
the
particles.
Gaussian beam will propagate throughout the air domain. Okay, and interact
Oh,
with
okay.
your gold nanoparticle. So it would be there inside the complete air domain as well. Okay,
Okay.
just
Okay, sir.
hold on.
Thank you.
Sir,
I'm getting a call.
uh,
Just hold on. I'm getting a call. Just hold on. Yeah, sorry.
uh, sir, this PML will it make sure that any retardation retardation in the after scattering it will get up. So that is the role,
Yeah,
right?
it will make
The
sure there is
PML.
no scattering, and the once the field interacts with the boundary. So I'll share you the blog. You can just learn more about it from this blog. It's very good in explaining this terminating domain conditions as well as terminating boundary. How do you terminate your boundaries so that there is no reflection from these boundaries or domains? Okay, so I'll just share with you this blog. Yeah, just hold on. I'm getting a call. It's an important call.
Hello, Jancy.
Yeah, sorry for the. Can you hear me now?
Yes, sir.
Yeah, sorry. So yeah, there were a few questions I couldn't address. Can you please Ask again. Are there any questions?
Sir, this is Jay Krishnan.
Yeah.
So, will you repeat the same, like, will you demonstrate the same model with the scattering boundary condition as well?
Doesn't means scattering is kind of lower level of boundary condition. If you see, did I share this with you? Link?
Yeah, you have shared this.
No. Ah, this I have shared, right? Yeah. So if you see this, I don't know why it is not opening, but if you see over here, right? So scattering boundary condition is a one step lower way to. So you
Yeah,
see, this
like
is the
the third.
PMLs are the best way to actually reduce the this reflection, that even for higher angle of incidence. So the only challenge with PML is that the computation time actually significantly increases. Other than that, there is no problem with PML. So uh, ideally, it's good to use PMLs instead of SBC any day.
Okay,
Okay.
okay.
So, PMLs are very good boundary conditions, very good domain conditions, like very beautiful, very helpful actually.
Okay,
Yeah,
thank you.
yeah.
Sir, when to use PML and when for instance, if I am using instead of a metal nanoparticle, if I am having a semiconductor, a quantum dot, and it is interacting with the light, so how do I decide which boundary condition is suitable? Because as the material changes, all the scattering, all that properties is different.
Hmm. No, yeah. In all the cases, you have to use PMLs for scattering boundary condition, for scattering field formulation. Okay.
Uh,
Yeah.
Sir,
Okay.
one more doubt, one more question.
Hmm.
Hello. So,
Yeah.
do we
Yeah.
need to define the RI for like PML also? A
Sorry.
refractive index for PML also, like either air or.
PML, you use physics control thing, so it actually takes from the air domain. So eventually, what happens is that here, if you see the mesh, actually, um yeah. So if you see that if you just zoom in over here, it's just a single small layer, and if you see the mesh, it will be kind of multiple layers eventually.
Okay.
Okay, like this. Now, what does happens internally is that in COMSOL, this is stretched apart. It becomes a huge domain internally. Okay, like hundreds of lengths of the wavelength. Okay, so and whatever uh, scattering it is going to reach to the PML is keeps on absorbing. Okay, for example, if you see this is the structure, okay, and you have a gold nanoparticle, and then you impinge an electromagnetic plane wave over here, you will get some kind of a scattering. Okay, some kind of scattering you will get. Now this scattering, once it interacts with this boundary, okay, it actually um, it actually reflects. We don't want that reflection.
Yes.
Okay, that is why we use a PML. Okay, which is an absorbing domain, which actually does away with this reflection. So it nicely absorbs all this. So you go there, it becomes zero, like this, in all the
Sir,
directions.
suppose if this
Yeah.
suppose this particle is located in air, and what is the need of a PML there? Because there is no boundary as such. The light will scattered out of the nanoparticle and it will propagate forward, right? Or in the either
No, no, no. It will
radiate it
forward, but
will.
this because this is a mathematical model, right? So we need to apply some boundary to all the boundary condition to all the
Oh,
boundaries. We cannot
and
leave any boundary
okay.
empty, otherwise it will be ill posed problem. Okay, so if you don't apply PMLs, it will be given as PEC, which is a worst boundary condition over here because PEC reflects completely. Okay, if you see over here, it's kind of makes it known tensor component actually becomes it's a perfect elliptic conductor and reflects 100%. Okay, so it will reflect a lot of electrical field from the surface which we don't want and will interact with our uh, simulation again. Okay, that's why we use PMLs.
Okay, sir. So, irrespective of the type of the nanoparticle, whenever the scattering is there, PMLs are it's
Yeah,
important.
PMLs is the way to go. Yeah. PMLs always use PMLs. If you are using scattered field formulation, you always use PMLs in all the in all the directions. Okay. If it's a circular
Okay.
thing, then you apply circular PMLs. The cylindrical thing, you apply cylindrical PMLs. Okay, that's good.
Sir,
So yeah,
if it
sorry.
is a PEC here, if it is
Yeah,
a perfect electrical conductor, won't it just short it?
sorry. Can you come again?
Yeah. If it is a perfect electrical conductor, won't it just short the field? Why would it reflect?
No, it actually acts as a perfect electric conductor. Means it acts as a metal, right? So any metals will always reflect. Will not
Will
short.
absorb and then reflect.
No, it will not even absorb because this means if it is a perfect means practical.
Lossless.
It is a this is a lossless electric conductor. Like perfect electric conductor is like lossless conductor, so it will always reflect
Never
the light
reflecting.
source. Yeah.
Okay.
If it's a lossy material that like TBC is also kind of a transition boundary condition is one of the lossless domain. Uh,
Mm-hmm.
Impedance boundary condition is also lossless domains. In those cases, like it will be absorbing a little and then reflecting. But all of them are metal, so perfect metal will always reflect.
Okay. And the second thing is,
Sir, I have
I'm not
one
very.
more doubt.
Yeah, Sujay, sorry. Yeah, you were saying second question. Yeah,
This PML, as I remember in can someone mute? I'm getting little.
yeah,
Yeah, in PML, I remember in Lumeric a long time ago, there was an option to then so you can actually give layer information, and you can increase the layer information and give specific variables to it and parameters, and then it will eventually increase or reduce your simulation time and also improve the simulation. Do we have an option to then change the PML, or
yeah.
it
So
will
the
be like,
scaling factor is similar to
or
what
that
you're
is the
saying.
same thing? Okay.
Scaling,
Uh-huh.
curvature parameters, and all those things. We can
Okay.
actually change over here, but by default we keep it usually one.
Okay.
Yeah, if you see something like significantly different, then you can explore this. But ideally,
Okay.
you should we keep it same over here. Yeah,
Okay. And this geometry is like suspended gold particles in
suspended.
air.
Yeah. So for
And you
simplicity, I
just
have made it as a suspended air particle, but you
understood.
can make it silicon in the bottom and then also
Understood.
simulate. So that is not
Makes
a
sense.
problem.
Okay. Thank you, sir.
Yeah. Yeah. So I think you had a question, Sabita.
Sir, if the nanoparticle size is like very small in the range of 25 to 50 nanometer, so in such case we there will be some absorption as well. So instead of scattering, normally we define it as an extinction.
Yeah.
The
No, this
process
is
as an
the
extinction.
scattering field formulation. In this also, you will able to calculate absorption. I will show you in some time when we do multiphysics. So you can also find out what is the
Okay.
absorption in. So this is just the approach name. Okay, but you can still calculate the absorption as well, extinction, exhaustion, everything you can calculate. Okay,
Thank you.
that's good.
Sir,
Yeah.
I am Gauri. Sir,
Hmm.
actually, in my domain, I am calculating for macro bending loss. For that
Micro
also,
or macro.
macro, sir, macro and micro.
Okay.
For that, the
So that is in the
formulation
case
is.
of optical fiber. So we are not talking about optical. This is completely different. Okay,
Yes, sir, that
optical
I can.
fiber. So tomorrow we will talk about macro bend. Means one of the ways to calculate or quantify macro bending losses
Okay, sir.
because of TIR and optical fiber. Yesterday also we talked about an optical fiber kind of geometry, and if you want to calculate the losses, macro bending losses, using mode analysis also you can do. So this is an example in COMSOL. If you just search for optical fiber bend in application library, if you go to file application library, search for optical fiber bend. Okay, in that you can actually see that that so because of the bend, how much is the losses would be calculated. You can find it out. Okay.
Okay, sir.
Yeah, but this one we so what was the context of your question? I couldn't understand.
Like in this formulation, it can be that scattering field, or it should be of any other thing like that
Yeah,
I
so
was
it depends
asking.
upon the cross section. Optical fiber again depends on the cross section.
Okay.
So if you are dealing with the transverse cross section that we discussed yesterday, like a vertical cut, then you need to do mode analysis. If you want to do everything in 3D, then you can do a ray optics that I will show you tomorrow. How to use the ray optics to launch the wave through a optical fiber.
Okay,
Okay,
sorry. Okay.
that's good.
So if I'm using in the transverse cross section means I don't want to like this physics can be the I don't want to change any physics.
Yeah, you can use mode analysis that we did yesterday.
Oh, okay, sir. Okay.
Using the same physics. You don't need to change anything. It should be full field only,
Oh,
not
okay, sir. Okay.
scattered field. Scattered field is for some kind of metal or dielectric, anything which actually could scatter, and you want to find the scattering field. The new
Okay.
parameter of scattering field you want to find out that time.
Okay, sir. Thank
Okay, looks good. Yeah, looks good. So now we have a beam radius of LD and not focusing at the center of this domain, transverse the electrical background electric field in x direction. Okay, and then just click on mesh. Okay, so you can see this. But one thing that we forgot was to mention here the wavelength. So you just mention here LD and not, and then in the wavelength domain, and then click on mesh to see the actual mesh. Okay, it looks okay. Not bad. Not it looks okay. Okay, so you can see over here the mesh for the PMLs. It's kind of layered mesh. Okay, so I will wait for a few moments for you guys to add this. Uh, First go to wavelength domain, add the wavelength LD and not that you have defined parameter, and then go to mesh and click on build all.
Excuse me, sir.
Yeah.
Sir, is the PML is only at the edge of the box,
Yes.
edges of the box. So then, how
Yes.
it will absorb all the excess energy at the
Not
like
excess energy. It
faces?
whatever is the scattered, it is there. For example, this is there in the center. It is there, and edge means over here on the outer domains. Everywhere is PML.
But at the face of the cube or that cuboid,
Huh.
what about
Yes.
that?
Yeah. So no problem.
You
You will
have not
launch from
applied.
here. Yeah.
Oh,
You will
okay.
launch from here inside. Yeah. You will
So
not
we
launch
need
from
not
here.
apply at the faces of the cuboid any PML.
Everywhere outside, all the outer domains, you apply PMLs.
Okay. Oh, it's like cage.
Yeah, it's like cage.
It looks
Correct.
like a cage.
Yeah.
So, but that's
Correct.
what
It's a
my
cage.
question
Yeah.
is. The face is
Hmm.
empty. The PML is empty at the face of the cuboid. At the so that's
No,
what
no,
I'm
no. It's
asking.
everywhere. It's PML actually. I don't know how can I show you.
Okay.
So this you can see, right? Everywhere it is applied.
Okay. Okay. Okay, sir.
Can you see
Okay.
this?
Understood.
Yeah.
Yes, sir.
Yeah.
Yes. Thank you.
Okay, that's good. So uh, that's it. So just click on compute and hopefully let us see how what is the degree of freedom, and perhaps you can let me compute first. I don't know how much would be the degree of freedom. Okay, it's around zero point 0.4 million, which is okay. But if you have system of 8 GB, then you can just close this system. Even mine is getting hanged, so don't run the system. Don't run this model. Uh, Just let me run this model. Because this is going to take a lot of RAM. Okay, we'll wait a few moments for you guys to uh, get something out. So anyone getting these results? Anyone?
Yes,
Yes,
sir.
sir.
Yes, yes.
Oh, good. That's great. But if your system is having like 8 GB, then might be having some problems. So just okay. I'll wait a few more moments for the others to see if they are getting something out. Okay. So how about others? Are they? You have any questions? Any errors?
Hello, sir.
Yeah.
It's still computing actually.
Yeah, but you are online. It's very good. If you are still computing, it usually gets hanged and it becomes very
Okay.
crazy. But it's fine. Means it's computing. It's you are still online. It's good. Yeah. Otherwise, the
Okay.
system will get hanged and you will not able to operate anything. Yeah.
Oh,
If it is a
okay.
low, kind of 8 GB is kind of bordering to 8 GB machine, then very difficult. Okay. Anyway, let us wait for a minute, 30 seconds more for people to compute. So as you can see that right now we are at a zero point 0.4 million. Okay, zero point 0.4 million degree of freedom. So that is a borderline of doing the simulation. Okay, so if you are on 0.5, zero point 0.6, then 8 to 16 GB is like okay to do it. Means 16 GB if you're there, then you can go stretch up till 1 million degree of freedom. But for a 8 GB machine, then zero point 0.5 million is the maximum that you should go. Should not go more
Sir,
than. Yeah.
this is a question. I have a question.
Mm-hmm.
Sir, I tried to do the animation,
Okay.
but it is not coming actually. The
Yeah,
animation is
I will
going
show
well.
that. Yeah, I will
Yeah.
come to that. Don't worry.
Okay, okay,
Yeah.
thank
Okay, if you use the norm E field, then there is no meaning in animation, right? Because normalized electrical field is a it's not a way. So I will show you one by one. Yeah. Mm. Okay.
And sir, a
Yeah.
question.
Yeah.
If the degree of freedom solved for is less than, say, for example, in my case, it is coming to 2,90,000 or so. So which is less than what you are saying. So is this definitely related to the kind of machine that I'm trying to? Maybe it is,
No,
maybe
no,
your
no. It
system is
should be
finer
almost the
than.
same for everyone. Yeah, it should be the
Okay.
same for mostly everyone. So if you are having reduced, then maybe some dimension change or wavelength that you're using might be different, or material properties that you're using that is different. Some change might be there.
Okay.
Okay. So what wavelength? It should be
Hello.
around that ballpark at least, around zero point 0.4 million.
No, sir, it is different for me. Uh, LDA not is set
How
to
about
500 nanometer in my case.
okay? How about others? Others are getting this degree of freedom as what value?
So, so I'm getting as yours
4 lakh.
4,23,460.
So it's not 4 lakh. Actually, it's 4. No, sorry, it's 4 lakh. Ah, sorry, yeah,
Yeah.
4 lakh. Correct, yeah, 4 lakh.
Yeah, it's
Yeah,
4 lakh in your
yeah,
case. Yeah.
4
Mine is 2
lakh
lakh.
28,000.
yeah, yeah. So around that value you should actually get. Otherwise, there's some change.
Mine is 10 lakh.
10 lakh. Oh wow, like 1 million degree of freedom. So, like you're still here in the call, so I'm happy. Usually this 1 million is difficult. I don't know. There will be some change. Some change would be definitely there in which is not there. But yeah, anyway, so you can see the video if you have missed something or something else. Okay, let us go through and find out what is happening. Okay, the important thing is that your electrical field is polarized in x direction. So now what I want to do is that I want to see the field that I have applied. Okay, the background field. To do that, there is a separate variable now which was not available. So for that, first let me uh, go to uh, okay. Okay, so let me add a data set. Okay, let me add data set of ZX view. So make a right click on data set, put cut plane, okay, and make a XZ plane, something like this. Okay, XZ plane along the x axis. Along means where I can see the x axis. Okay, that's a cut plane that I have created with plane XZ. Okay, I'll wait for a few moments for you guys to create this cut plane.
Sir, my simulation dynamically does not show the cut plane as of now. So is there a,
No, if you right
do I
click
have
on
to
data
fix?
set, you will get a cut plane, right? No,
Yes, sir. But like the one it is
just
showing in
click
your
on plot.
simulation, the red color, it is.
Okay, no.
Oh,
Sorry,
okay.
yeah, go to cut plane and click on plot.
Okay, okay. Okay.
Okay, so now you are going to evaluate at this particular cross section. So just right click on results, click on 2D plot group now because you are going to discuss on that particular cut plane, 2D plot group, and automatically you can see that cut plane has come over here. Okay, so don't need to worry. Just right click on the 2D plot group and click on surface plot. Okay, right click on 2D plot group, click on the surface plot, and over here you just click on background. Just search for background. You will see this ewfd.ebx. Just click on this replace expression and search for the background, and then search for ebx. This is the wave that we are launching. Okay, that's very important. The wave that we are launching, that is ebx. Okay, we'll just share that with you as well, with everyone. Okay, so now if you happen to model a very big geometry, then you will see the convergence and divergence over here. So here it's not that prominent, but here also you can actually see something actually converging and then diverging. If you have a breadth to be a little bit more, right, then you can nicely see that convergence and divergence of that laser beam. Okay, this is the background. So this is background electrical field, which means that it is not the field which is interacting with any domain. So you can go to the animation and click on player. Okay, again go to sequence type as data extension, repeat as forever and click on play. Okay, and this is the first thing that you should check once your system is computed, that whether the Gaussian beam is propagating or not. Okay, are you getting a standing wave, or is your model this electromagnetic plane is propagating or not, or some kind of reflection is happening somewhere. Very important to check this. So here you are able to see, right? So it's propagating. right? So this is very important to check always. Okay. Yeah, you have a question? Anyone? Sabita, you have a question?
Sir,
Yes.
Yeah.
yes, sir. Sir, in this model, this model does it take into account of any surface plasmon excitation or anything?
Yeah, surface plasmonics are always there included because we are solving for Maxwell's equation. So the plasmonic effects that we see on the surface, it's present. So I will come into that surface currents, all those things I will come into it in some time. Okay.
So the background electric field which you are showing, it's I can see that does it include the field in between the nanoparticle?
Yes, 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 yes. It will assume that this is a
Currently
air domain, completely vacuum domain, and then it will launch this background. This background field is just to know how does it look like in air domain. So it is not taking into consideration this nanoparticle. Okay. Yeah. So once we talk about scattering field, then it will talk about this the scattered field, that is the reflected field. Okay. Okay, looks good. So now you can just enable this height
Hello.
expression. Yeah, sorry.
So I'm getting an error in that animation. It is
Okay.
showing. It is saying as when I run it, an animation must contain at least 2 frames.
Yeah, you need to click dynamic data extension. Have you clicked
Yeah.
on dynamic data? Have you change the sequence type to dynamic data extension?
1 second.
Okay. So
I have changed, but it is still computing again.
yeah, just make it for repeat to forever and then
Huh.
click on this. Maybe your system is a little bit low memory, so it's taking more time,
Yeah,
but
yeah.
no problem. You'll get it.
Okay.
Yeah.
Yeah, fine.
Okay.
Thank you.
Now let us go and find the scattering. To find the
Excuse me,
scattering,
sir.
what you need to do? Yeah.
Um, Sir, sorry for interruption. Sir, actually,
No
in the
problem. Tell me.
same thing, uh, like in the place of air, if we put water, and also if we apply some external motion to it, like the medium is like a water medium is rotating, maybe a magnetic stirrer. So, is it, and then we are launching a laser light towards the this particular solution. So how do, is it going to be the same, or it is going to change if we put this kind of system or something like that? I'm
That
just
depends upon the
doubt.
material property of the water. For example, is it a conducting material, conducting fluid, or it is a magnetic fluid, or it is a non-conducting fluid? If it is non-conducting fluid, then it will not do anything.
sir, I also
I
have a
mean,
question here. Suppose the particles are executing a Brownian motion when how does
Okay, no, that is
assume the
very
ball
complex
nanoparticles
actually.
there?
This is only for a single instant of that particular thing. So if you want to introduce the motion instantaneously do, then it's very difficult. This is only for a specific time instant. This is the particular, but you can add water to the background, so that's not a problem. So you can change it to the water domain and then launch the wave. That should not be a problem. But this it is assuming that this domain is constant at this particular place. What you can do is that you can do a parametric sweep of this motion with whatever place that you moving away and close, and then you can see what is the enhancement based on that motion. But doing this time dependent is very difficult.
so only we can do is the distance of the particles, between the
Yeah, you
distance
can
only we can
move these
change that.
particles wherever you want. Yeah, in parametric sweep, you can do a parametric sweep with this position. You can keep on moving this. If one particle can be up, another particle can be down, and then they're coming close to each other and then moving away. Like that, you can do a parametric sweep of its position. You can change the position based on this position. These
So
positions you can keep on.
parametric sweep of the distance, isn't it?
No. Parametric sweep of its position. Okay, based on that, the two of them will change. So this you can write here
Okay, okay,
x
sir. Thank you.
coordinates of your spheres. Okay,
Yes, sir. Thank you, sir.
that's good. So uh, uh, we can try it out means in the second half today. So yeah, any more questions? So instead of this background field, you can just duplicate this 2D plot group, and you can also write the scattered field, which is the most important part. So just search for this replace expression and search for relative. Okay, this relative is the scattered field. So relative x, y, and z components. So we'll search for rel z, that is the scattered field. Okay, and click on plot and you can see the scattered field. Okay, you can also see the x component, y component, all the components of your scattered field. Now you know that your propagation is happening from bottom to top. Okay, so you can now see the animation for the scattered field, and then you can for the x component of your scattered field, and then extension, and you can see that it's actually in opposite direction, right? You're launching your wave from the bottom. That's where the scattering is happening in the towards the bottom direction, and the top some energy is passing through this structure inwardly. Okay, so some energy is passing through it, and then also scattering. It will take some time, of course, because it is calculating for all the phase of this simulation. But yeah, once it is done, you can see a very nice animation. Also, you can see that because these gold nanoparticles are completely metal, so very low fields are there, electrical fields are there inside. Okay.
So for the second 2D plot group that we added, will it by default take the same 2D cut plane that we gave for the
Yeah,
surface?
yeah. Correct. So in that you can use this EWFD dot E X. Okay, not the EZ, because Z component is not that significant. So as X component of the scattered field is more significant. So I'm just trying to take that.
Excuse me, sir. What did you interpret with this plot 3? Can you repeat?
Sorry.
What did you interpret with this graph
Plot 3
3?
is for
Just
scattering.
plot 3.
So once if you see the animation, it is developing. So you'll get to know it's kind of very intuitive. It's like two stones in a water river. You're trying to have a ripple through this from the bottom to the top, and then this is scattering back. Okay, so maybe this is not that intuitive. Whereas I can, if I enable this height expression, it will be more better. Trying to animation of this. So here what is happening is that because of these two gold nanoparticle, you are actually putting energy from the bottom. Okay, so let me just take this to one try this one. Okay, so what you are doing is that you are trying to give an input from the bottom. This is the plane wave that you are trying to excite, the particular polarization in x direction. Now, because of these two nanoparticles over here, what is happening is that some energy is actually going through these two because of this channel, and some of them is getting reflected or scattered back. There is both forward scattering and backward scattering, right? So both the scattering is actually happening because of these nanoparticles. Okay, and what you are trying to do is based upon, if you use the relative variable, only then you are able to find the scattering of the field. Now based on scattering field, you can find out what is the scattering coefficients and other extinction coefficient and scattering coefficients. One example that I shared yesterday that uses the same scattering field to kind of find its scattering coefficient and my coefficient, for example. You want to do that also you can get. Okay.
Okay, sir. Thank you.
Yeah. Any more questions?
Uh, Excuse me, sir. Sir, I am not getting the second plot of
Did
this.
you plot the EWFD dot RELEX?
Yes, sir. 1 minute.
Okay.
Surface 1, EWFD dot RL EZ or EX, sir?
EX. Yeah, you plot EX and you can enable the height expression
Okay.
to even if you
One
don't
minute.
height expression, then you can visualize it, but might be a little bit difficult. But if you use this height expression, then it's more intuitive.
But
So here you can
yes.
see that little bit of energy is
Okay.
getting backscattered. Some of the energy is getting forward, and then some of the energy is getting backscattered as well. Okay, we are propagating from
Yes.
bottom to the top. Yeah.
Yes. Now it's coming.
Sir,
Yeah. Yeah.
Sujay here. If you go to this
Mhm.
height expression, the scale shows that the red one, the energy 0.3 volt per meter, and the lowest one is minus 0.6 per volt per meter.
Yeah. So this
Right?
is the
0.3
scaled
to
up. You can see this is
correct.
scale factor. So if you want to see the actual one, then you just make it one. Okay, so
Uh-huh.
it's not that much actually. So because it's to visualize something better, they actually put it.
Sure.
Yeah.
But then can you use the same scale? Because when I go to the animation one, I
Mhm.
don't see. I only see the peaks and troughs at the particles, but the rest of the peaks are almost gone. You see?
Yeah, yeah. So that has to do with
Yes.
this values actually. If you make the values
Correct.
same, then you will see that same
Yeah.
thing.
Is it possible? Because
Mhm.
to get the same view, this
Yeah,
thing a
yeah,
little
yeah.
bit different because I
Correct, correct. Yeah, yeah. That I understand. How to get the same view? I also don't know this one.
or
Yeah.
maybe reduce the other one. I don't know. Something.
Yeah, that also is possible if you reduce that. So that is possible. If you go to this, you should get the range operation over here. Then you can change the color range. Okay, from
Okay.
here you can actually vary and make it
Yeah.
almost the same that is mentioned over there. Okay. Yeah.
Okay. I'll try it.
Yeah. Okay, looks good. So the next point is the enhancement factor. So that we will take in the next session in half an hour. Uh, about how can we actually, because if you see over here, if you disable it over here, so you can actually if you plot the norm E part now. So let me just plot the yeah. So actually, scattering is defined by this, not scattering. The enhancement is defined by the square of the absolute values of the electrical field. So you can see that there's a electrical field is enhanced in the center of both of them, right? So in the next half, we'll talk about this one. If you move this nanoparticle close to each other, what is the scattered field increasing or decreasing? All those things will work out. Okay,
Hello, sir.
that's good.
Sir,
Yeah.
actually, my system was hanged out. Actually, which lambda D0, which L lambda H0 you have used?
Yeah, LDA naught is 500 nanometers.
500. Okay, okay.
Yeah, yeah. Yeah, but yeah, if your system is getting hanged, then if you want, you can try it out. But yeah, how much is the RAM in
My
your
system,
system?
yeah, 16 GB. I don't know why it is sitting
Okay,
here.
okay. Yeah, maybe
Okay,
the
I'm.
geometry just see that it is the same thing. It's around 500 to 1000 nanometers, and the gold
Yes, sir.
nanoparticles are this one, and then this is the air. Okay. See the mesh
Okay,
as well.
okay.
Mesh should not be much involved. Okay, that's good.
Okay, let me try once more then. Okay,
Yeah,
sir.
sure. Okay, then see you at 5 o'clock, everyone. Take care. Bye. Hello and welcome again to the next session. Let me know if there are any questions or doubt to what we have discussed till now. Okay. I see the comments uh, about this meta mems filter. Yeah. So meta materials is also possible in COMSOL. Yeah. So yeah. Yeah. Sujay, you want to add something?
Yeah, so Chetan here added a winter school program
Yes. Yes.
where you are the host of the program.
Yes. Yes. Yes.
I just went through. So we were discussing. So we just went through this some of the topics. And they look
Hmm.
certainly interesting to a lot of people here who are attending.
That's
Um,
correct. Yeah.
and the point is, unfortunately, because of location and semester start, it would be difficult for some
Hmm.
or most of us to attend. Is there a possibility to at least partly attend it online or later on show at least get some material or some recordings or something? Maybe if it is paid, it is also fine, I guess. But
Yeah. Yeah.
if it is something, because it would just kickstart some. For example, this console course, we all are in a different level of study or level of expertise, but certainly every one of us got one or multiple things that could help us fast, like improve our
Yes.
level. So I don't know. Maybe if it is possible, you can then see the possibility or feasibility of it from your end.
Yeah, definitely. We can see if we can have it online as well. So I have to request the organizers to see how if we can do it online. So ideally, we the first edition also we did it in the mid of December actually. That's the time when usually many people are on leave. No problem, but usually in Chennai there are a lot of torrential rains during the mid Decembers and end of December. So heavy
Mhm.
cyclones and all those things happen. So we shifted it to the first week of Jan because a lot of things need to be organized and you have to call a lot of people. So if something like torrential rains happens and cyclone happens, then everything goes under the carpet. So that's why we
Okay.
shifted to the first second week of January. Usually it's
Mhm.
very pleasant in the second week of January. People who are aware of Chennai. So yeah, this online, yeah, definitely I will discuss with the organizers and I can get back to you guys. Let us see. So we can float a form online and see if people who are interested for online participation they can fill that form. So we will invite you guys once the school starts and the recorded session also. We wanted to do it hybrid mode. That is the way you can actually have a better reach, of course. So, but there are a lot of things that because we are a very few bunch of people who are organizing it, so it becomes very taxing for us to organizing both the hybrid and or offline as well as online part. But yeah, definitely will see if I will just request the organizers, other organizers as well. And let's see how does it go. And through email we will actually communicate you guys. I mean,
And sir, is it
yeah.
since we are here, I actually I don't want to bother you too much and don't want to be unprofessional in like later on contact you for multiple things. But is it then sometime possible that once every 6 months, if we are stuck with some problem for really long time and not able to answer or get a answer out of it, can we just drop you some email? And is it like if you don't have time, you can certainly tell us that.
Hmm.
But otherwise,
Yeah,
would it be fine or would it be
definitely.
bad?
Yeah, you can drop. Yeah, yeah. No, don't worry. Yeah, so you can drop an email. So I will try my best to
Sure.
respond. Yeah, so I cannot guarantee that I will be able to respond because it's a little bit tight because I
I
and now
understand.
I've shifted. If I would have been working in COMSOL, then it would have been a different thing. But now I moved to clinical diagnosis and different work actually altogether.
Uh-huh.
So it doesn't overlap to my work. So but yeah, if I have time, then I definitely will respond. Should not
So
be a
thank you,
problem.
sir.
Yeah, yeah. Okay. That's good. Yeah. So the way the winter school biomedical optics is structured is that we have 5 days. The first day, people who do not know, so the first day is on tissue optics, and second day is with um, spectroscopy. Third day is tissue imaging. Fourth day is microscopy, and fifth day is optical biosensors. And we also have few people from statistics to come and deliver a talk on statistics as well. Yeah, looks good. So looks good. So let us go forward from our discussion there. Yeah, I've just seen the chat. If there are any more questions, yes, I think Sujay has got a LinkedIn as well. Okay, looks good. So I will just go through that as well. It's good. Okay, so yeah, if there are no more questions, let us move forward. Try to understand the enhancement factors.
So can you explain the cut plane process once again in short if possible?
Yeah, so if you see our solutions are actually on the node points. Okay, so that's important to know that node points means the mesh. You see this, these are the node point. So our mesh, the node points of the mesh actually has the solution, and then all the other places are interpolated based on the discretization function that we defined over here. If you remember, we discussed in the first class, first session. Okay, and so the solution is present throughout the whole domain, but I am interested to only see in a particular cross section of it, right? Of course, not in the complete domain. So one way to do that is to have a cut plane, right? The cut plane, if you see now, why I'm using this x z is because if you see in 3D, this is my x and this is my z. Okay, x z plane. So I can do a cross section cut like this one. Okay, because it will involve the cut of both the spheres, gold nanoparticle spheres. Okay, so I do a cut plane cut like x z, make the coordinate to be 0. So I can just move a little bit up and down by making the depth. I can change of the cut plane by changing the y coordinate 0. That will be 0 right now. Okay, and that's it. Right? That's what you wanted to know, right? Or what else you wanted to know about cut plane? How do we create the cut plane? Just right click on data
Then what
cut.
what I have to do next?
Okay,
Actually, I missed that part
so
due
you
to my
created
submission
cut
was
plane.
not complete.
Were you able to
Yes, sir.
create cut plane?
Yes, sir. Yes, sir.
Okay, just right click on the results, add 2D plot group. Okay, you can also create 3D plot group. In that also you can add, but then you cannot make height expression, right? So if you want to do a height expression kind of a feeling of the how it propagates in 3D, then you need to use 2D plot group. And in this 2D plot group 4, you can see the automatic cut plane comes. So you don't need to worry about here because there's only single 2D geometry over here, no, 2D solution over here. So automatically understands that it needs to call the cut plane 1, and then right click on 2D plot group to create a surface plot. Okay, and then you can put whatever expression that you want to put over here. So if you want to see the background field, the EBX is the background field. Okay, so this background field, we want to have the relative term, that is the scattering field. Then you have RELEX, scattered field. Okay, and then norm. So it's like background field equal to is equal to the if you see the EX over here. So if you draw EX uh, plus RELEX, then you actually should get the background field. No, is it the background field or not? No, I think I've done something. Is it EX minus this one? Mm, background field minus this, I think EWFT dot EBX minus this equal to. So it's a combination. These three variable actually they have some kind of relationship. I keep on forgetting this, but they are having a relationship that one of them equal minus this one equal to the third term. So yeah, so is a background field minus the EWEX is equal to the uh, scattered field. So I think this is the scattered field, right? Yeah, if you plot that without the absorption. But yeah, so that's fine. So let us focus on this enhancement. So now I want to quantify what is the enhancement. Okay. Okay. So you can see what I need to do is that I want to find what is the electrical field in the center. Okay. So how do I do it? I can so if you remember, the equation of the enhancement is something on the similar lines of enhancement is equal to the absolute of the field that you have right now divided by the uh, incident.
Input.
Yeah, input, correct. Yeah. So input in electrical field is actually 1 actually. So it eventually turns out to be whatever you have the field over here right now, output or scattered field is actually becomes the enhancement factor. Okay. So now I want to know at the center what is the enhancement factor. So exactly at the center what is the is the enhancement factor. So one way is to just right click on the derived values and just click on global the point evaluation. But point, there's no point over here, right? Over here. So let me just put, what should I do? What should I do? What should I do?
Sir, if you put this in point evaluation, this wireframe comes out, and then there are a lot of points where you can then.
No, but there's no point in the center, right? We didn't create any point in the
Ah,
center.
okay. Okay.
Yeah. So I'm
Can you
just
have a
trying.
point without any structure?
Yeah. So there is something known as probe, point probe,
Mhm.
that used to be there. So you don't need to add that point, but you can evaluate at that particular point probe. So, but that also we didn't add. So I'm just thinking, what should I do? Point matrix evaluation here. Can I? So what you need to do is you need to create a data set again. Okay. Just right click on data set and you can create a point 3D. Something like point 3D should be there. Cut point 3D. Yeah. Okay. This is a cut point 3D. So here you can write 0, 0, 0. So it means that this is the point that you want to evaluate. So this is the point that has come, right? Okay, I'll wait for a few moments for you guys to add this cut point 3D if you're interested. Okay, and then point evaluation in the data set you need to change it to the, okay, here actually you can see the coordinates as well, so should not be a problem. Okay, you can plot and evaluate, but what point you want to evaluate? Point evaluation. Okay. Okay. I don't know what did I change earlier, but now it should come. You see, if you create a, what did I change? Okay, I didn't change anything. What was I saying? Anyway, so point evaluation 1, you just need to go to dataset and select cut point 3D1. And over here, you can just mention the same thing, absolute of EWFD dot RELEX the whole square. Okay, so then you should actually get the same thing that you mentioned over here, right? So it's a, don't worry about the units because eventually it becomes uh, so if I divide by 1 volt per meter square, the whole thing becomes square, so its units actually becomes the same. Okay, so it becomes unitless, right? So because right now the input electrical field is equal to 1. Why 1? Because you have mentioned here. Okay, It's not like what I'm just mentioning here, but so just mention it over here for you guys to look around. So, and you click on plot, and you can see this is the enhanced. So it's actually giving input as 1, but now it is actually 2. Okay. So now what you can do is that you can move that um, uh, the spheres little bit close by, okay, and then see what is the enhancement field. You can do a parametric sweep as well of that distance.
So this RELAX represents the scattered field.
Scattered field, yes, that is the main field of interest in when you are doing scattered field formulation. At the scattered field, what is after the interaction with the nanoparticle, how is the scattered field and how it is doing. So yeah.
Sir, for simplicity, did you take the incident to be of unit strength or?
Yeah, that is for simplicity. By default, it will give you 1 only.
Okay.
Yeah, but that doesn't matter, right? If you give 2, you will get 4, right? Means not 4 means,
Yes, yes.
but factor would be always the same. So enhancement factor would be you're interested, right? So doesn't matter what amplitude you give unless until like something is going to melt.
Yeah.
Excuse me, sir.
Yeah.
Sir, actually, this point evaluation, what actually did to it? I'm not
Yeah. So
getting.
what I wanted to do is that I want to find the electrical enhanced field in the center of this 2 nanoparticle.
Okay.
Okay. Yeah. So
Yes, sir.
yeah.
In the
Yeah. So
point
what?
evaluation, after
Hmm.
adding the equation, so when I evaluate it, it's nothing actually happening.
Have you changed to cut point 3D here?
Uh, yes, sir. Cut point 3D1.
Yeah, if you place
One
the cut
moment.
point 3D1, are you able to see the red dot between this?
At cut point 3D1, the dot is there, sir.
Okay, but
But
here if you
point
evaluate
evaluation,
in table, what are you getting? Nothing.
okay, there we have to see. It is
Yeah, table in the table
1.6470.
1.64.
Yes, sir.
But
Understood.
enhanced, there's some enhancement is there, right? Yeah, that's fine. Something is there. So yeah, but
Okay.
yeah,
Yes, sir.
so it should
Thank
be
you.
almost like this, almost. But yeah, it should be same actually around that same value, but maybe there's some difference with the material properties or some changes would be there. But yeah, should not be
Uh,
much problem.
Okay, sir.
Yeah. Okay.
Sir, I have a question.
Yeah.
Sir, in COMSOL, is it possible to so in this particular scenario, at the midpoint between this nanoparticle, is it possible to put one dipole, some atomic dipole, and then
Yeah. So there is an option on electric dipole. You can right click on electromagnetic waves frequency domain, and there is an option of dipole. Yeah, electric point dipole or magnetic point dipole. Okay, so you can put it, and then you can give some kind of a uh, magnitude of the dipole or direction of the dipole, and you can see how does it.
so depending upon some particular atom having this much dipole strength, I can those values I can give there
Yeah, you
basically.
can. Yeah, you but yeah. So you can see that how people have done it. I have not used much of the electric point dipole. Usually we just find this enhancement factor, and that's how it's used to be. But yeah, so you can just see how people have done this thing. So why you want to add electric dipole? Like,
And it's a scenario want to recreate for surface enhanced Raman spectroscopy, in which a
oh, okay,
atom or
okay.
a molecule is kept in between the.
Okay, I see. So yeah, I think this kind of work would have already been done. So try to find out some journal papers who were using COMSOL multiphysics to so you try to replicate that particular paper completely and see the same results you are getting it or not first. And once you're
Okay.
getting it, then you keep on tuning your other parameters.
Okay.
Okay,
Thank you.
that's good. So the next point would be, for example, I want to see the enhancement from here to here. Okay, from here to here I want to see the enhancement. In that case, you just need to right click on dataset, click on cut line 3D one. Okay, and then you just click
Hello,
on
sir.
plot. Yeah.
Can I terminate this call and rejoin again? It's like I'm not able to see. Your screen is still.
Yeah, you can join again. Yeah. I'm just trying to plot it from 10, maybe 15, maybe 20, then 25, and minus 25. So you can see this is the line that I've plotted. Now, along this line, I want to see how the enhancement is changing, right? So in that case, I can just right click on results, 1D plot group, global, and over here, I choose that, okay, line graph, cut line 3D. This should, oh, not global, sorry. You have to choose line graph. Okay, in that line graph, I will get this option of cut line 3D, and I put this expression over here, and here you should be able to see how this enhancement factor is kind of going from here to here. Okay, again, always good would be to put asterisk this line marker at evaluate point, so that based on the mesh, so you can see that enhancement is in the center is around almost around 1.92, but at the edges it's kind of very high. Okay, so if I bring that both the nanoparticle close to each other, perhaps this enhancement could actually further increase. Okay, for example, if I right now it is around 80, I can make it like 70, and sphere 2 also 70, a little bit more closer, for example. Okay, even maybe further closer, for example 60 and minus 60, and then I see the model, and then again I run the study just to see how it is actually. You can do this parametric sweep of these values as well. Okay, instead of this 60 minus 60, you can do a sweep of 60 to 80 with a step of 5, for example. Then you can see the enhancement field, how it is increasing as it is going closer to each other. Okay, so this course is just to give a flavor of how you can do a lot of things based on your application. Okay, so you can do a lot of things once you uh, know the basics. Yeah.
Sir, is there any tutorial which handles the parametric sweep of position?
Yeah, there would be some, definitely. I don't remember, but on top of the head, I don't remember. Well, I can show you. It's not that difficult. In the recorded, it will be go there. Okay, so you can see now.
Oh, hello.
Yeah.
Sir, this is Deepak. Sir, can you please repeat the process once again? Actually, I missed some part.
Which
And
process you want me to repeat?
so the field in between the two sphere. Uh,
Yeah.
so
So the
you
field in between the both sphere. For this is a cross section view. So I'm just writing the square of my relative scattering field, the whole square, and I'm getting this kind of field enhancement. Okay. So this is the equation I've also messaged in the chat box. If you can you see that in the chat box?
yes, sir, I can see it.
Yeah, you can see that. So the same thing I'm just copy pasted over here, and then I want to do at the center of the sphere. I want how much is the enhancement because of the gold nanoparticle. So if I want to evaluate a point evaluation, you can see earlier when the separation distance was around 60 nanometers, it was around 2, but now it is 21, almost like 20 times the electrical field that you give input, right? So significant increase in electrical field. You can also see the line graph. Actually, line graph will not make much sense because it has gone inside, right? So but almost is in over here between the spheres is almost like actually it's not correct because the variation of them are so high that it's not showing the actual curve. Okay, well, if I have it like this, maybe 8 to 8. Okay, at that time it will be fine, better. So you can see the actual increase that is happening,
Okay.
but it should be symmetric. I don't know why. But yeah, it's almost the same value. You can see that it's 21 to 21, not much variation.
Sir, can you please just see the repeat the steps once again? Actually, I missed some steps. So can you please repeat it? First, cut line 3D one, then where should I
Yeah,
go? Uh,
yeah.
like this.
Cut line 3D1 is first you create, and then you create a 1D plot group and then line graph. I
Okay.
actually we don't have much time, so you can anyway see the recording. I will share it with the night, and you can see
Okay.
the
Okay. Sir.
recording. And if you still find it difficult, then you can let me know
Okay.
tomorrow.
Okay.
Also, I can. Okay,
Okay.
so
Sure.
not a problem. Yeah.
Got
Okay. So what I wanted to show you that is a parametric sweep. That would be something new. So what I'm going to do is I need to mention over here minus 50 minus the offset. Okay, the offset is the parameter that I'm saying that it is the distance between two of them. So if the offset is around 10 nanometers, okay, so this is total actually around minus 60 nanometers. Okay, it's almost the same. Okay, so here also I can write it over here, but instead of minus I will write it as plus in both the direction. It will almost be the same. So the distance is so the distance is nothing but 2 times the offset. Okay, distance between this the optical sorry this 2 nanoparticle is 2 times the offset, 20 nanometers in this case, right? You understand, right? So just if you just right click on the geometry and see this, measure the points, it would be around 20 nanometers. You can see, right? So what I can do is that I can either go actually parametric sweep the distance, or I can go okay, distance is twice of this one. So there are two ways of going about. So either you can parametric sweep the distance or the offset. So you need to, if you want to do the distance, then you make it like 20 nanometers is the total distance, and then d offset is nothing but this one divided by 2. Okay, so total distance is actually between this is around 20 nanometers. This is 20 nanometers now, right? Now if I change it, for example, 40 nanometers and then click on build all, then my geometry will change, and now the distance is between these two are 40 nanometers. You can check it by right clicking on the geometry and clicking on measure and clicking on point and clicking on over here. You can see that it's 40 nanometers. Okay, so now whatever distance I mentioned over here, for example, it is now 60 nanometers. Click on build all. Now this distance between the two nanoparticles is 60 nanometers. Okay, so I can do a parametric sweep on the distance, and then automatically my nanoparticle will keep on moving away. So just right click on the study one, and click on parametric sweep, and add this as distance over here, and I can add so what I'll tell COMSOL is to start with the distance between them to be around 20 nanometers with a step of 5 nanometers and till around 60 nanometers. But this would be like too much computation time because for each of them it's taking around a minute. Okay, so maybe I'll just try for this 4 of this, maybe it takes 4 minutes. Hopefully before 6 o'clock we can complete this. Okay, and then I click on compute. So now we have 4 solutions, and for all the 4 solutions I can try to see what is the enhancement field factors, and definitely as the both the nanoparticles are moving closer to each other, you will see that the enhancement field is kind of increasing, right? So like this, you can change the motion of the two particles in whatever direction that you want. Okay, you can have two parameters together, one for the coordinates of your first particle, second for the coordinates of the second particle. So it's kind of, you will see that how it is moving across something.
Sir, is it possible to define a particular trajectory for this particle through an
Yeah, that's what I'm
equation?
saying. For trajectory involves the positioning of the coordinates of both the points, right? So you can actually do a parametric sweep of their position.
Okay,
Okay,
this both are
position means
different.
coordinates. Yeah, position defined by coordinates, right? So
Hmm.
the coordinates of that is if you see the sphere one, it has x, y, and z in the base points, right? So that those
Hmm.
becomes the coordinates. So x1 prime, x2 prime, x3 prime would be for the first sphere. The x1 double prime, x2 double prime, x3 double prime would be for the second sphere, and then that you can actually define. So the parametric sweep you can actually define based on the position of each of the trajectories of both of them.
Okay, so that is totally different. This is a parametric sweep between the
Yeah,
distance.
no, correct, correct. So for example, one is the trajectory followed by this is the trajectory followed by the one of it, and another trajectory followed is something like this one. Okay, so basically each of them is having points, right? So
Hmm.
right, so each of them will have a coordinates, right? So
Yes.
each of them will have a x, y, z coordinate, right? So you need to give that. This would be for one parameter. This would be for the second parameter, second particle. Okay, and that keeps on changing. So you can first run that model for this parametric sweep. The parametric sweep will have
Hmm.
this parameter. Then second would be
Okay.
for this parameter. Then third would be for this parameter. Like that you can do. So it will have breaking down the actual problem into small parts.
Okay.
Okay, yeah. Yeah. Any more questions we have? Yeah, this is a convergence plot. I didn't touch upon this as of till now, but usually the relative tolerance that it stops by it is around 10 power minus 3. So if you are lying somewhere below this after some time, that means you are in good hands. So it starts from very high value and then kind of goes down like this. So this is for 20 nanometers. I don't know,
Hello, sir.
10, 20 or how much? Yeah, sorry, tell me.
Yeah, this Pratik. Actually, my question is not related to it. Sir, actually, yesterday you have the mode analysis of optical fiber for 2D cross section.
Yeah,
You have done. Yeah, actually,
yeah.
if I want to do that mode analysis for a graded index fiber, like that was the stable index fiber. But if I want to do with the graded index fiber, then how you input the refractive index? Like it is varying from the.
Yeah, sorry.
Yeah,
So,
actually.
is Pratik right? So, Pratik, let me just complete this and then I will talk about this mode analysis. If I don't want to jump now, I'm just
Okay,
trying to
okay.
conclude this one in 5 minutes. Okay, then we can ask about that. Okay.
Okay, sir.
Okay, looks good. So now we have completed this solution, and you can see that the solution is for four of them. So this is the parametric study one solution one. So I need to change my cut plane from study one to parametric solution one so that I can access the I can access the all the parameter values. Where is this one? So here you can see. So this is for different distance. So this is very close by to each other. So if we are very close by to each other. Okay, this guy is gone. So it is from parent. Let me check from here. Yeah. So here you can see these are very close by to each other, and then this is little bit far away. and then this is even farther away. Okay, so you can have more refined mesh over here to have even more accurate. Okay, and then the cut point 3D, use the parametric solution, and then point solution. In that point solution you can have for all of them. You can see now the plot it in the table. So as the okay, this is x-axis should be distance, y-axis plotting column should be this value. Yeah, so here you can see, so as the distance is increasing, okay, distance between them is increasing, their enhancement factor is decreasing, right? So this is what I wanted to show you. Okay, that also makes sense. As the distance between the both nanosphere is decreasing, enhancement factor is increasing. Okay, so this is also a very important curve that you find in many journal papers. Like how does it enhancement factor changes based on the distance between the different particles and dimensions and all those things. With this kind of parametric sweep you can actually do. Okay, another thing that I wanted to show you, that is the currents, because that is the main important part, that is plasmonics. So people are talking about plasmonic effects. Can you show me the plasmonics? So basically plasmonics is nothing but the currents, the superficial currents. So the way to visualize the currents would be to first see the select only the gold nanoparticle. Okay, to do that I need to cut plane. Yeah, I need to, this cut plane is, I need to only select my spheres. So right now it is through all of them. Let me see how does it happen. So I will just try to see the currents, and there's a norm j variable, so just double click on it. Okay, so you can see this one. Okay, so this, you can see this currents on the surface is kind of very significantly more as compared to the outer domains. If you want to only visualize the inner domains, you can also should be able to do that. Let me just see. Yeah, you cannot do by this one. Okay, just let me see how can I show you that one. Maybe I can use multi-slice here and then select only the inner domains. Okay, here I select, do a selection and choose only the domains. Okay, and over here I norm j. Okay, so here this is the currents that you see over here. So again, you can use boundary layer mesh to improve this, but this is the currents that we were discussing about, this skin depth over here. So based on skin depth, you can see how much is the intensity kind of dying down as you go inside. Okay, so this is that skin depth part, plasmonic effect parts. So actually we are able to simulate the plasmonics over here. You can also see the current, how it is flowing inside this. So it would be some in particular direction. If you do arrow volume and again select this nanoparticles, and you select what you want to plot is as a particular current. Okay, so ideally the current should be more prominent on the boundaries of it. I don't know why we are getting the complete domain. Ideally it should be more prominent on the surfaces, so you can see that it's dying down very quickly. Yeah, I don't know, maybe I'm doing something.
Is it also for, again, just simplicity that you took a 2D cut plane? Because if I'm really interested in the surface currents, then I'm just analyzing current in a plane which is basically like a line profile here. If I, in that plane, this is just like a line profile, right? The current is like a line profile here in this plane. But generally, because it's a surface phenomena, I should be having something like a volume volume
Yeah,
kind of a thing.
yeah. So this is a volume only. So what I want to show that because the arrow line that we see over here, its length is directly proportional to the magnitude. Okay.
Mm.
Here you can see that it's more prominent over here, right?
Yes, sir.
So here it's more prominent as you go inside, it is getting lower. So the more
Yeah.
currents are more prominent over here as
Yes.
compared to what you see over here. So that is nothing but because of this skin depth of this particular material. Yeah, I was wanted to show that maybe if you choose this only this one, I just duplicate it and then I make a selection of this guy and then put a cut plane on this guy. I get this guy over here and then I create a 2D cut plane of this second guy, arrow surface, and then I put current. But then still it's going almost the. Okay, now you can see, right? So you can see that the current that is happening over here, it's like almost like 0.8, right? So yeah, that is because our mesh is not good actually. So if I improve the mesh, right, then you will see a more prominent display. So current would be like significantly more as compared to this one. Here it's like only transitioning from 0.8 to 0.5, but in actually the center it will be kind of going very low. It actually depends on skin depth, but it will be significantly lower because the poor mesh that you're having inside, it's actually, so you can have to do some user control mesh and mesh the inner sphere with boundary layer mesh inwards, then you will see it. Okay. One more thing that I wanted to show, because of these losses in a conducting media, you guys know what will happen? Any guess? There will be some kind of losses. Yes, if you guys must be knowing it. So there will be some losses you can see. So because of the high currents, there will be losses. Okay, this is watt per meter square, and the same loss you can actually couple it with heat transfer interface. This is what a part of multiphysics node that I wanted to cover. So multiphysics is because you want to couple these losses, and you can take these losses into heat transfer. You can add a physics, and then you can see what is the rise in temperature on these nanoparticles, and you can see, you can quantify it, what is the rise in temperature, how much degree rise is there in the, if it is like switched on for some time, and evaluate. You can see how much the deformation on this nanoparticles because of the rising temperature, the thermal expansion as well. Okay.
You said about this rising temperature and this time scale, whether do we get any idea of the time scale? Like, I'm exciting
Yeah,
with
so
this
that's a good
laser.
question. Actually, the time scale is kind of because the time scale of electromagnetics problem is in order of nanoseconds, femtoseconds. But in the case of heat transfer, things to develop some more temperature, it takes around seconds or minutes, right? So there is specific study known as uh, frequency stationary study. Okay, so that helps you to do that. Now, if you are interested, I can share you the paper that we wrote some time back on this multiphysics analysis. There is a photoacoustic problem. I don't know if it's available or not. It's a numerical analysis. It talks about this coupling in details. It couples four physics actually. Electrical. We use event interface to make a pulses of light source. So short pulse of light source will give you rise in temperature, and that short pulse of chunk of light source, chunk of rise of increase in temperature gives you a structural deformation, which actually leads you the photoacoustic
Uh,
wave. So
so this gold and all are having low specific heat capacity, so time scale will be also a little bit shorter, right?
sorry.
Since the gold and silver, all of them are having low specific heat capacity, so this heating process is also
Yeah.
relatively
So it based
faster, I
on the
believe.
material. Correct. So all this material, specific heat, everything will come into the picture. Correct. Yeah. All of this will actually come into the picture. Yeah. Yeah.
So,
Yeah.
sorry to interrupt.
Yeah, tell me.
So the thing is, I am working on TAM plasmons,
Okay.
but I haven't seen any blogs related to the TAM plasmons.
Cam?
TAM plasmons.
Can you spell that? I also don't know about that.
TAM plasmons.
So what is special about Thames Plasmon? I don't know.
It's like it's not unlike surface plasmon only, but it will exist at the interface between a metal and DBR structure.
Okay, you can share me some. I don't know. Means you can share me the details. I actually don't know about it. Can you come
It's
again? Means you can share your screen and show me what yours.
yeah. Just a minute, sir. Can I
No.
show you a paper?
Yeah, you can
Or a
quickly show
paper?
me that. Yeah, you just look into it. Yeah. Yeah, I think Pratik, you had also one question, right, about the mode field. So we can take it now. Pratik, or who was?
Yes,
Like,
yes, yes.
so what was you talking about that? Can you come again? Sorry.
Actually, sir, if I want to mode field analysis of the graded index fiber,
Okay.
then we need to put the refractive index like gradually increasing or decreasing.
Yeah,
Understand
yeah.
that. So how can we put the refractive index?
Yeah, so there's a spatially varying refractive index you can put. That's not a problem. So you can put it in a file and then call, for example, or you can write an equation, or you can use a piecewise function in COMSOL as a function of radius.
Okay, is there any tutorial video which I have to put? Actually,
Yeah, means I can show you one example. I think I will show you in my screen.
Sir, can I share my screen?
Yeah, just a minute. Let me just complete his
Yeah,
Pratik's.
sure.
This one. So even if you go over here, if you go to File, Application Gallery, which lens was it? It was some kind of a lens. I keep on forgetting that. Some lens example, engine lens or no? The ray optics.
Bloomberg lens, sir.
Leuenberg lens. Yeah, this one. So here actually, here the refractive index is spatially varied across this domain over here. So it's like some kind of function it's written, right? So either you can write a function, piecewise linear function, or you can write mm, you can call piecewise function. So here you can see the refractive index is like this one. So as you go on radially outwards, the refractive index kind of decreases.
oh,
Okay. Yeah. So I will share this. So either you can use this one, or you can also use this piecewise function. So if you right click on, if you go to this, if you can see my screen, just right click on the definition, and then go to functions, and then this piecewise is there. Okay. So just click on piecewise, and then you can write what is the start and end of that radius, and what is the function. Function means what is the refractive index.
okay.
Okay, like the multiple things you can write. And then you can call that as a function. This function name you can call it as a function of radius while you're assigning the refractive index, like what is given in the Leuenberg example. Okay.
Okay, sir. Thank you.
Sir, I have a doubt. Kavit on this side, so.
Yeah. So I will go to one by one. So I think Jai Krishnan was asking something. Then I will. Jai Krishnan was sharing some
Yeah, I'll
your
share my
screen.
screen. Yeah. So this is the structure that I'm actually working on. So can you see this?
Yeah, yeah.
So which is a one-dimensional DBR. On top of it, I have to coat a metal surface. So for only DBR, I
How
can
thick
able
is the
to
metal?
how
Thick is the
around
metal.
between 30 to 60 nanometers.
Which metal is it?
Uh, which is actually this is actually gold, but I can show you one paper which I have simulated. Can I show you that?
Yeah, yeah, you can show that.
I'll show you the paper. So this is the structure, sir. A. So A is
Mm-hmm.
actually the structure, and the D is the actual graph that I want to get, the reflectance graph.
Mm-hmm.
So what the problem that I'm facing is for the DBR, if I'm using the port condition itself, I'm getting the reflection like this.
Mm-hmm.
But when I'm adding the metal, I'm not getting the reflection like this. So I don't
Yeah,
know
no,
what.
no. For metal, you need to see the skin depth and apply boundary layers. Perhaps tomorrow
Okay.
I can show you how to apply boundary layers. Or
Okay.
alternatively, if you don't want to do this harakiri, you can actually add use this instead of modeling volumetric metal, you use TBC, transition boundary condition, and then
Okay.
assign the properties of that gold as TBC. You mentioned what is the thickness in TBC.
Okay.
So usually TBC is assigned for those material where whose skin depth is almost equal to its physical thickness. For
Okay.
example, if they are almost matching, then TBC is a good way. So instead of modeling the thin volumetric domain, you just model it as boundary and apply TBC in the top.
Okay.
See how it is happening. Okay,
Okay. Okay. Thank you.
that's good. Yeah, hi Kavita, you had a question.
Yes, sir. Sir, I have designed a single mode fiber and multi-mode fiber combined structure, and I
Hmm.
want to observe the phenomena of self-imaging or multiple interference there.
Okay.
And by varying the length of the multi-mode fiber, I want to see the imaging position at the different
So
position and
length
use.
is very difficult to model in COMSOL. That is the biggest challenge, right?
So we can't model that in the COMSOL single mode and multi-mode
Uh,
fiber.
yeah, it's very challenging to model length as well as and so in 3D you want to model, right?
No, sir, I want to model in 2D. I just want to have the images,
But
self-imaging points.
how can this work in 2D because it's a multimodal, right? So
Sir,
well,
I
you
have
can.
designed
Mhm.
it. Can I show that?
Yeah, yeah. So how does this the which cross section is this one, longitudinal or transverse cross section?
Longitudinal, sir, longitudinal.
Okay, but how does this transverse cross section look like?
Sir, first we have the single mode section, then multi-mode section. There is a diameter difference between these two.
Yeah. Do you have any schematic of that?
So currently I haven't found that in any paper. I'm
No, no, but
designing
did
it for
you
the
make
first
any
time.
schematic out of it? Like how does it look like? I mean, well, like single mode is becoming two double modes.
The light propagates from the single mode, then it goes to the multi-mode fiber. At the end, we have again have the single mode fiber, and the ultimate propagation is from the single mode, multi-mode, single mode. Currently, I'm showing you the multi-mode, single mode structure.
Multi-mode, single mode.
Yeah, currently it is multi-mode, single mode, which I'm showing you because I have
Okay, okay. I
tried to
see.
design you in the part of multi-mode, single
Okay,
mode,
okay. Yeah.
multi-mode,
So it's always
and
good to
I
show
just
some
broke out.
schematic. Otherwise, it's very difficult to understand what is happening. Can you go to the material section
Schematic
here?
in the
What is
sensor. Yeah.
schematic means? What is what? Means here I just some blocks for me, right? I don't understand. Maybe you're working for this on maybe 6 months, 1 year, but for
Yes,
someone
sir.
new, it's very difficult to understand. Yeah. Okay, I see. This
Yes,
is the cladding. Okay.
yes, sir.
Core is the center one. Okay. Air also you've given.
So that PML layer.
Okay. So how you're launching this using port?
Yes, sir.
No, I don't think so. Port would be a okay using numeric port. Okay, fine. Numeric port, but you apply at the end also numeric port. No, okay, you have PML because you don't want to do this. Oh, what port two is what? Okay, so port two you are limiting it to one particular mode. So you don't
Yes,
want to
sir.
limit it to that particular mode. You can apply disable this port too. Okay, and just let PML absorb all the domains, all the energy. You always don't need to have all ports, right? So SBC, but PMLs, can you show me in definitions? How does that PML look like? But even in this, because this is a cross section, so it's
Okay.
kind of a ridge. You understand? No, and if this thing is extending in of plane, out of plane, so it's not a circular thing. Eventually, it's kind of a rectangle thing which is going in infinity towards in and out outside. Okay, just make sure that that is the one. Okay,
Yes, sir.
yeah.
Yes, sir. Yes, sir.
But this is small geometry. It's in
So can you
micrometers. So
repeat that
in
point?
you can also do it in 3D. That if you want to do a spherical simulation, like how the field observed the spherical thing. But yeah, this looks okay. Yeah,
Okay, sir.
this you can try to see. The mesh is important. How are you doing the mesh? You do not need to go for a physics control mesh. You can go physics control mesh. Any particular reason you're doing for this? What wavelength are you using?
1550, sir.
That's still huge. So in this case, right, what I will tell, I will help you. See, because this looks to be very difficult and time consuming. So you go to this electromagnetic waves frequency domain. Okay. First you do because you have done some manual meshing, right? In that you have maintained it is lambda by
Yes,
5,
sir.
right?
Yes,
Yeah.
sir.
So you do Control Z, roll back to your user control mesh. So Control Z you do 2 times. So you go to that original version. Yeah. This is one, right? Good, good. So now you go to electromagnetic wave frequency
Yes, sir.
domain. Okay. Go to this discretization. Yeah. Instead of quadratic, you use the next version. What is the next?
Quintic.
Yeah. Okay, and then you go in the mesh. The way to mesh would be not lambda by 5 now by n. It would be lambda by 2.5 by n. Okay, so change this from lambda by 5 to lambda by 2.5 each everywhere, and then you try to run the mesh and see it would be a little bit better in model. It will not take much time, and you will get almost the similar kind of results that you will get. Okay, it will save you a lot of time. Okay, you can also try to squeeze this from the both the sides, because having such a long core for the single mode, I don't know if there are no propagation loss. Are there any losses in your domain? Is it a lossy domain?
No, sir. Currently
Yeah.
there is no,
Then
sir.
it doesn't make
There
sense,
is
right, to have
lossless.
such a 10 micrometer, 20 micrometer long single mode fiber, and almost again 20 meter, 20 30 meter long multi-mode fiber. You can have just 1 micrometer. Do you understand,
Okay,
right?
sir.
Because that's what you want to see now, how
Okay,
much
sir.
mode is there. Means you can start
Okay.
with 1 micrometer, just the thickness would be around 5 micrometer maximum. The center you can have the
Okay, sir.
transition, then keep on increasing. Right? Start with a simple thing
Okay,
and then
sir.
you can try on keep on increasing. Okay, that's good.
Okay, sir.
Thank you.
Thank you, sir.
So just a comment, and so I don't know the particulars of Kavita's design, but
Hmm.
the multi-mode fiber at 1550 nanometer with a typical core cladding refractive index and with 15 micrometer core radius would lead to like V number of 10, and the number of modes would be 100 approximately. Or sorry, yeah, 100 approximately. And then you couple it directly like core to core, center to center to 10 or 8
Yeah,
micrometer, you will have like
yeah,
80% loss. And
yeah.
is
That
it
is
is
true.
it possible? Is it
Now you
possible
can
like
use some kind of couplers. Actually, there are a few
so
couplers
is
that
in
are
yeah,
yeah.
in between
That
it
could,
is so just a
maybe they have
suggestion to
something, but they are
Kavita.
not showing us.
That is possible.
No,
That
sir.
is
It's not like that.
Yeah,
Because
there's
I'm
some.
also
Maybe you can use some
designing.
kind of grating coupling. People usually use with that thing. Yeah,
and then the
Because
second
as
thing
it's a
because
trade
complete
secret.
fiber, so it's not
Yeah.
possible to use that inside of that coupler. It's a complete fiber structure.
Okay, okay. I see. I see. It's
it's a
Actually,
but to
sir,
but coupled. Okay.
So
sometimes
it's not
sometimes the
possible
SMA
to use it.
multi-mode fiber and SMA that make an interference pattern. For
okay,
interferometer, someone can use SMA, MM,
okay.
SMA.
I see. Yeah.
But the follow-up question, is it then possible to like to know whether at least the higher energy mode or fundamental mode from the multi-mode fiber is actually propagating, or and how much percentage of it is going to the single mode? Is it like, because if the main energy mode is lost, then it would be really difficult to
Sir, I'm getting this
get
couple
the
of.
data out in the single mode.
Yeah. Sujay, your question is directed to Kavita or
Sir,
me, or Sabita, you
To
want to add something?
to you, but anyway, let Kalvita finish and then I can.
Okay. Yeah, I understood, Sujay, what you were saying about this. I think again, so we need to have multiple ports as we discussed. So with that, you can get to know about this, how much energy mode conversion power is there for each of these transition of modes. I think that should be possible. Yeah, but I don't know. You have to try it out. I don't know.
Sir, I also don't know that because your question is very much genuine. I also don't know. I
So
don't have any idea.
Kavita, we are unable to hear you. So yeah, till the time, Sabita, you can. You are asking something.
sir, yes, I have history. The model of this gold nanoparticles field enhancement calculation. Suppose if I want to replace gold nanoparticle, the structure of the gold nanoparticle by a core shell, like the core is a
By a
gold or silver. Core shell,
by
core
a
and shell.
core shell. Okay, okay,
Mm.
okay.
So,
Which
so there
material?
is a layer of so inside there is a metal like gold or silver, and it is coated with SiO2. Then do the same
Okay.
calculation.
Yeah, you
So,
can do that.
uh,
Yeah, you can physically add that layer by using layers.
okay,
Yeah, I've seen people doing it, so I think it should be possible. Yes,
using
Sujay has a question.
layers order, right?
Yeah, yeah. I mean, so I've seen papers, not models, but papers are there with.
Okay.
Yes, yes, so Sujay has a suggestion about thermo-optic photon switch changing. Yeah, I think yeah, that is also possible. Yeah, yeah. Without
No,
MEMS.
no. This is a follow up. This is the next question. So this is no suggestion. This is a different topic. So I didn't
Okay,
bother.
so a
I didn't.
question.
I just
Okay,
wrote it.
but without MEMS module is difficult because MEMS module has this all this modules required for this coupling. So MEMS, so
But
for
the
coupling
heater
from,
heater does the same thing, right? So if you have a lithium niobate structure and the heater on top, I have seen papers with they have this.
yeah. So maybe you can do
Um,
some manual coupling might be required then. If you don't want to use MEMS
mhm,
module, some manual
mhm,
coupling might be required then. Yeah, direct
mhm.
coupling might not be available. Manual coupling
So
should
then
be
I just
available.
have to import the thermal physics module and photonic. So yeah. So multiple. I have never worked with this, so maybe I can try this multiple physics. Import the multiple physics modules and then do the simulation, right? One
Yeah,
by
maybe I
one.
can try tomorrow as a simple example. I wanted to
Yeah,
cover
that would
that
be
today,
good.
but we had a lot of questions on this. So I couldn't cover multi physics. Tomorrow I can
Hmm.
actually cover this part as well. Should not be a problem.
Thanks.
Okay, that's good. Then you have trial license, so you can see what license it is being used. For example, you can go to if you go to COMSOL multiphysics, if you go to
I think you
file,
start the screen.
yeah,
Yeah, yeah, okay.
yeah. So if you go to this file, license, and user products, if you see file, then license and user products, you can see which modules are being currently used. So as you have trial lessons, you can get to know what modules are being used. Okay, so tomorrow if you do multiphysics, you can see what modules are going to get disabled. Disabled means which are the modules which are being used. Okay, looks good. Okay, then looks good for today's session. So let us meet again tomorrow to take this forward to the last day of our session. So in the end of tomorrow's session, we also have a small kind of feedback and assessment form. That will have for around 15-20 minutes max.
Sir, can I share my screen for the result I have
Yeah,
got?
yeah. Okay. Yeah, we saw that result actually. Yeah, but I don't know how much it makes sense. So what are you plotting exactly? Y
Sir,
component of electrical X
yes,
Y.
sir.
Okay. So how you give port one numeric port? But did you
Yes, sir.
you can see what is the electric mode field that you're observing? Next plot. No, no, in the electrical field bottom below this electrical field plot. electric mode field port 1. Yeah, not that one. Electric field mode field in the result section. So this is the mode that you want to propagate
Yes,
inside.
sir.
Okay. So can you open this inside the triangle? What is the function that it is plotting? Yeah, go inside the line plot. Okay, interesting. Yeah, but yeah. So it looks like this. Doesn't look. If you go to electrical field again, okay, and just open that. What function are you plotting in electrical field plot? So it starts with the same thing actually. EY. Okay, I see. Then it kind of messes up. Yeah. So intuitively it doesn't look wrong actually. So it looks just like to be fine, but yeah. But you see the difference in time
Should I change
computation
it
as
to
compared to
normal E?
before, or it's same time it was taking?
Yes, sir. No, so it computes very fast.
Very fast now. Yeah. So you can play around now a
Intuitively,
little bit.
yes, sir.
Comparatively, the results should not be actually very much. No, yeah, means you can change with EY, EX actually, and see how it happens. Usually there should be 3 peaks. I don't know why there are 4 peaks actually. Yeah. Okay, EZ. How does it look like EZ? Do we get Z component as well? These are 3 peaks, right? So here the 3 peaks are there. So the middle peak, middle is actually able to couple. The
Yes, sir.
other
And
two
the
are
other two
actually
are in the
getting
class.
lost.
Yes, sir.
Correct. This actually makes sense. Something. Okay. You can also see the animation and see there are any reflections or not. Okay. Go to animation player. Smoothly, at least it should go like it should like go in one direction. There should not be any reflections or kind of standing waves. You can just close this study and physics node. So it would be in the right hand
Yes,
side.
sir.
Yeah, in the right hand side, the study node and physics node actually on the right hand side. Yeah, like extreme right hand side. Add study, add physics is there. Just close that one. Yeah, it takes the space of this GUI, right? That's what I'm saying. You can just zoom into this core region.
So currently it's
Oh yeah, you don't have a mouse, so you cannot do it. Can you zoom into this core region? You cannot. Yeah. Now run again. Okay, this is fine. So you see the propagation, right?
yes, sir.
Yeah, so that makes sense then. Yeah, that looks good. Yeah, that's good. You can, yeah, this is a good model. Should not be a problem. It looks intuitive actually. Okay,
Yes, sir.
that's good. Yeah, okay. Then let's meet tomorrow then to take this discussion forward. Thank you. Take care. Bye bye.
Thank you, sir. Bye bye.
Bye bye.
Thank you, sir.
Thank you, sir.
Thanks. Bye.
Thank you, sir.